Okay, welcome back. So before the break, we saw that we had, based on the 2x2 table that we have here, and based on exposure status and the outcome, we have the odds of disease being present among those exposed is pi of 1 over 1 minus pi of 1. And the odds of disease among those who are not exposed is pi of 0 over 1 minus pi of 0. Now, let's recall that we define the logit as the log of pi of x over 1 minus pi of x. So the logit is actually the log of the odds, or the log odds. So specifically, the logit for people who are exposed is the log of the odds for the exposed group, and the logit for individuals who are not exposed is the log of the odds for the unexposed group. Now, many of you have heard about the measure of effect called the odds ratio. And interestingly, although it's not often taught this way, and often it's taught in introductory courses that the odds ratio is from a 2x2 table, simply A times D over B times C, you'll be happy to know that the odds ratio is really the ratio of the odds. So here we have the odds ratio, and the odds ratio is defined as the odds of disease for people who are exposed, there it is in the numerator, divided by the odds of disease for people who are not exposed. There it is in the denominator. So the odds ratio is really the ratio of the odds. And the log of the odds ratio, log odds ratio, is equal to the log of all of this. Okay, the log of the odds for those exposed over the odds for those not exposed. And when you take the log of the ratio, you get the log of the numerator, which is the logit for those exposed, minus the logit for those not exposed. So the log of the odds ratio is the logit difference. Okay, so let's now directly compute the odds ratio. Okay, so we know what the odds ratio is. It's right here. Okay, the odds ratio is this. So I can actually write this a bit differently. I can write this as pi of 1 times 1 minus pi of 0 divided by pi of 0 times 1 minus pi of 1. Okay, so just a little bit of algebra. So here we have this. Here is pi of 1. This is the probability that someone who's exposed gets the disease, times, and this is the probability that someone who is not exposed doesn't get the disease, divided by, here's the probability that someone who is exposed, someone who's not exposed gets the disease, times the probability that someone who is exposed does not get the disease. Okay, I basically exactly took this expression and I simply plugged in the expressions for these probabilities into this formula, and I got this. Now at first this looks fairly intimidating until we realize that this denominator and this denominator are the same, so they cancel. And this denominator and this denominator are the same, so they cancel. And what we're left with is e to the beta naught plus beta 1 over e to the beta naught. And when we divide these, remember we subtract the exponents, we're left with e to the beta 1. Now, I don't know when you're watching this. It could be late at night or it could be early in the morning. But normally when people are wide awake, they get very excited about this result. This is an amazing result from logistic regression, that for a logistic regression model, when you have a binary independent variable, the odds ratio is simply e to the beta 1. Okay, so if you tell me the coefficient from the logistic regression model and you push the E button, you get the odds ratio. That is really an explanation for why the logistic regression model has become such an amazingly popular tool in epidemiologic research, in criminology, and sociology, and in any field where you have things like exposures and responses. When you have a binary exposure and a binary response, e to the beta 1 is the odds ratio. It's an amazing result. And the log difference, or log odds ratio, or the logit difference, or log odds ratio, is the log of e to the beta 1, or just beta 1. So the actual coefficient that comes out of a logistic regression model is the log of the odds ratio. Okay? And remember, e to the coefficient is the odds ratio. So let's take an example to illustrate this, and again we're going to look at the CHD age data, and we're going to create a new variable, and we'll call this new variable x, and x takes on the value 1 or 0, and it'll take on the value 1 if the individual has the risk factor, and in this case the risk factor is age greater than or equal to 55. And the individual does not have the risk factor if age is less than 55. Okay, and this results in this 2x2 table. So in this 2x2 table we can see that for those who have the risk factor, we can see there are 27 individuals in the data set whose age is 55 or older. You can see that 21 of the 27 have evidence of coronary heart disease. But among those who are less than 55, 73 of those, 22 of 73 have coronary heart disease. So you can see just from the, the relative risk point of view that the odds ratio is greater, or not the odds ratio, but the risk of CHD is greater among people with the risk factor than it is for people without the risk factor. But now we're going to want to take these data and compute the odds ratio and everything else from it in a crude way. I mean, in a crude way, we simply take the odds ratio is 21 times 51 over 22 times 6. 21 times 51 over 22 times 6. That's the A times D over B times C that we learn is the definition of the odds ratio from a 2x2 table. And that odds ratio in this case is equal to 8.11. Okay, 8.11. And what does that tell us? What's the interpretation of that? Think about that for a second, and how would you interpret the 8.11? If you said that that people who are older have 8 times higher risk of CHD than people who are younger, you would have given the wrong answer. Okay, the correct answer is that the odds of CHD is 8 times higher among those who are older than it is among those who are younger. Okay, so odds ratio is just what it says. It's the ratio of odds. It's not the relative risk. And it's a mistake that's commonly made and commonly misinterpreted. The logistic regression model does not produce a relative risk. It produces an odds ratio. However, odds ratios are good proxies for relative risks under certain circumstances, and particularly when the disease is a rare disease, so the prevalence is low. Okay? In this case, it's not particularly low, because in this case, a large percentage of the individuals have CHD. So the odds ratio would not be a good proxy for the relative risk. What if I wanted to, what if I wanted to write down the likelihood for these data? Well, the likelihood for these data would be written down as the probability of getting what we got. Okay, and so likelihood function would be, we have 21 people who had the risk factor who also had the disease. So that's pi of 1. We have 21 of those. And we have 6 people who had the risk factor but didn't have the disease. So that's 1 minus pi of 1, and we have 6 of those. And so on. We have 22 people who did not have the risk factor but did have the disease, so it's pi of 0 to the 22nd power. And finally, 1 minus pi of 0 to the 51st power is the people who didn't have the risk factor but didn't have the disease. Together, that's 100 terms in the product, and that's what the likelihood function looks like. So let's have a break, and then when we come back, we'll look at the computer output for logistic regression in this situation.